Let's talk about the story of sequences, series, power series so far. Remember, a sequence is a list, and a sequence converges if the terms have a limit. A series is a sum, and a series converges if the sum is finite. And a power series is a function where the question is different. For what values of the input do we get a convergent series? So where does the power series converge? Because we can plug all kinds of stuff into it. The first stop on the story, the first story beat, was the sequence of partial sums, our brute force approach. Just try to analyze the problem by calculating stuff. If the sequence of partial sums of a series converges, then the series converges. Moreover, the limit of the sequence is the sum of the series. This could get difficult because it's numerically looking at a series, numerically looking at a sequence, and a sequence has an infinite number of terms. So this could become very intensive unless the sequence converges rather quickly. But it gives us something that we can calculate with a lot of power, with some computing power. This led us to our first important conclusion, and that's the test for divergence. If the limit of the terms is not zero, the series diverges. This was an important thing to recognize. If the limit of the terms is not zero, then the series converges. Sorry. If the limit of the terms is not zero, then the series diverges. From this, we get the contrapositive that if a series converges, then the limit of the terms must equal zero. But we don't get the inverse, where if the limit of the terms is equal to zero, the series converges. We don't get that one. Great that I'm recording a bunch of things that aren't too true, especially when I keep mixing up converges or diverges, unless I'm like really concentrating on what I'm saying. It's like we need two completely different words, not just like converges and diverges. But that's all right. It's like we should call something that's like that's more distinctive, like convergence series. We don't say convergence series. The series is Batman, and if the series diverges, we say the series is Joker. It's more of a distinction, at least visually. But anyway, I digress. So that was our first important realization. If the terms don't go to zero, then the series diverges. Since there are series that have where the limit of the terms is equal to zero and the series still diverges, our favorite one being the harmonic series, we drew this conclusion. It's not that the terms go to zero, it's how the terms go to zero. So the question now, moving forward, when we're looking at convergence of series, is how do these terms go to zero? Because those are the ones that we care about. Those are the ones that might converge or might diverge. If the terms don't go to zero, we are done. That is a divergent series. So now the question is, we really want to focus on, it's not that the terms go to zero, it's how the terms go to zero. So the next thing that we observe, this led us to think about how this is happening. How do these terms go to zero? And we came up with this integral test. We came up with it, like no one had heard of it before yesterday. But we thought about the integral test. We say, well, this series is a sum. We're adding a bunch of things up. So there must be integrals at some point, and that is true. Integrals is just addition or accumulation, so it's a natural fit. In an integral, we're usually trying to cram an infinite number of things into a finite space by making them thinner and thinner. Here, they're all going to have the same width. The delta x is always going to be 1, but there's going to be an infinite number of them. So at least we have a place to put the plus. So this is the different kind of infinity that we talked about before. So yesterday, we used the integral test to show that the harmonic series does diverge. That the harmonic series is the left endpoint approximation of the improper integral from 1 to infinity of 1 over x dx, which we saw diverge. There's an infinite amount of area under the function 1 over x, and above the interval from 1 to infinity. Since the harmonic series is an overestimation of that area, we concluded that the harmonic series must diverge. The sum of the harmonic series must be infinite. That was a little bit sloppy. It doesn't have a sum because we would get infinity. All right. So let's now apply the integral test to a series that at least I told you converge. The series 1 over n squared converges. So let's apply the integral test to this series to see that happening. So we're gonna take the integral from 1 to infinity of 1 over x squared dx. We make a continuous function out of the general term of our series. Now we would find here we would find the antiderivative and plug in the endpoints, but one of our endpoints isn't even a point, it's an infinity. So we have to do a little bit of a workaround. We'll take the limits as b goes to infinity of the integral from 1 to b of 1 over x to x. This is how we plug in infinity. We can't plug in infinity. This is how we plug in infinity. We take the limit and b goes to it. So what we're going to notice here is that when we integrate, when we add 1 to the exponent, we see that the x is still going to be in the denominator. So this is an x to the -2. So the antiderivative is negative x to the -1. So what we notice here is that when we add 1 to the exponent, that x stays in the denominator. From a let's just calculate standpoint, we end up with 1, because as b goes to infinity minus 1 over b, that goes to 0. We can interpret this as the area under the curve 1 over x squared and above the interval from 1 to infinity, we have an area of 1. So this is going to start looking a lot like we had yesterday. So the area under the curve 1 over x squared and above the interval from 1 to infinity that area is equal to 1. What we're going to notice is that the series 1 over n squared is the right approximation, the right endpoint approximation of the area under this curve with a delta x of 1. So this series actually, we're off by a little bit. This series is the right endpoint approximation with a delta x of 1. So if I have this first delta x at 2, I've got this area is 1/4. And then at 3, I've got this area is 1/9. And then at 4, I've got this area is 1/16. And we can see that we are underestimating the area. Now, you might notice that where's the 1 in all this? So you're right. The series 1 over n squared is the right endpoint approximation. The series of 1 over n squared, if we add 1, if we subtract 1 from it, it's missing that first term. Our right endpoint approximation is getting the area under, but it's starting with a 1/4, not a 1. So the series 1 over n squared is definitely less than 1 plus the integral from 1 to infinity. The integral from 1 to infinity of 1 over x squared to x is equal to 1. So the series 1 over n squared is definitely less than 2. So here we can visualize how this works, how the integral test works. So since we got a 1 for the improper integral, we would say the improper integral converges. Therefore, the series converges by the integral test. This seems like a lot because we have this new mechanical thing, this improper integral, which some of you may have noticed showed up in chapter 7. It's like, hey, are we going to talk about this? And I'm like, oh, yeah, just not right now. Because I knew it was coming up in the integral test. I like foreshadowing the story, but that's just like way too much. Introduce a character in chapter 7 that's not going to show up until chapter 9. When it seems like you've completely shifted gears. I don't know, maybe I should do that more. Marvel seems to be really good at it. Oh, here's the next movie. And then they have like some mid-credit scene, which is just an ad for the next movie. And it's like, oh, I wonder what the next movie is going to be. It's going to be, it looks like it's going to be this, but now they just tell us what the next movie is going to be. Here's phase 10 of the Marvel Cinematic Universe. So here's what we want to grab from this. Here's what we want to grab from this. Notice that when we integrated 1 over nx squared, the x was still in the denominator. So when b goes to infinity, that term went to 0. That's what we want to notice. Note that the x was still in the denominator. It happens right here. Here is the interesting shit. I have to point it out because this is interesting shit in a math class, and it's not that interesting. So I got to point it out. After we integrate, x is still in the denominator. So when b goes to infinity, that term goes to 0. After we integrate, x is still in the denominator because we add 1 to the exponent. We started off with exponent that was more than 1. So when we add 1 to the exponent, the x stays in the denominator. So when b goes to infinity, that term goes to 0, and then the improper integral converges. This is why the harmonic series is so cool, because the harmonic series is the boundary of this happening. The harmonic series sits right at the boundary of what happened right here. The harmonic series is right at the boundary of this adding of x being in the denominator. So this is why the harmonic series is where we start. It's like the first series that doesn't get to 0 fast enough. Because if instead of integrating 1 over x, we integrated 1 over x to the 1.000001, that still converges. So if we have the improper integral from 1 to infinity of 1 over, I'm not going to use that many zeros, 1 to the 1.01 dx. When we integrate, we add 1 to the exponents. And the x is still in the denominator. So this improper integral converges because the x is still in the denominator. But if that exponent, if it's 1 over x to the something slightly less than 1, then when we add 1 to the exponent through integration, that x pops up into the numerator, and then everything goes to infinity. So if I have the integral from 1 to infinity of dx over x to the 0.99, when we add 1 to the exponent, x is in the numerator. And now when we integrate from 1 to infinity, I get infinity minus 1, which diverges. And right in the middle is the antiderivative of 1 over x being the natural log of x, which goes to infinity as x goes to infinity. This is why the harmonic series is so important. It's that boundary. It's like the first thing that doesn't get to 0 fast enough. So the way I think of it is harmonic series is like the first one that doesn't get to 0 fast enough. One over x to the 1 plus epsilon converges. Improper integral converges. 1 over x to the 1 minus epsilon diverges. Right at the boundary is 1 over x, turns into natural log, that goes to infinity. What's the boundary between the stuff that converges and the stuff that diverges? So it's a very good description on what gets to 0 fast enough. Because remember, the question is not that the terms go to 0. The question is how the terms go to 0. This, recognizing this from our integral text, leads us to the next part, next conclusion. Where am I at? 4? I'm going to call this 3. So 3 was the integral test. So like 3a is the P series. Because I want to think of P series as a corollary to the integral test. So the P series goes like this. The series 1 over n to the P converges for P strictly greater than 1 and diverges otherwise. So the integral test is giving us this very important conclusion. We don't see the import of this conclusion. So this gives us some series that we can recognize as converging or diverging just by looking at them. The series 1 over n cubed converges. If we had to justify it, we would say this is a p series with p equal to 3, which is greater than 1. If we had to justify it. If you have to justify that, you're probably having a conversation with a teacher, in which case just do the integral test. So if you're like, well, it's a p series with p equal to 3, which is greater than 1, therefore 1 over n to the third converges. And then if someone's like, oh, well, how do you know that? It's first of all, probably me, at which point you roll your eyes, like in your mind, just in your mind, you go, ugh, and then just do an integral test, because it's 1 over x cubed. They're just like, oh, fine, I'll do the integral test. And then you integrate it. Then if the person is like, oh, well, what's this integral test that you're talking about? This is not a person that you should be having this conversation. And you should be like, oh, just get out. If you're not going to make an effort, just go. I wouldn't do that. That would just be, if I'm like, oh, how do you know? This p-series stuff. They'll be like, oh, fine, I'll just do the fucking integral test. And I go, oh, okay, now I understand. But if someone's like, well, you have to justify the integral test to me. They're not arguing in good faith. They can do this. You know what I mean? Don't argue with people that won't argue in good faith. This is why you don't argue with flat earthers. They aren't going to be arguing in good faith. I really truly believe that these people at their core, these flat earthers at their core, know that the fucking earth is round. And they're just trying to be obstinate because they're not arguing in good faith, because they run their own experiments buying expensive equipment. Their experiments prove that their conclusion is flawed. They go out, they prove that the earth is not flat, and then they still refuse to believe that the earth is not, is round. Like, oh, you did your own science on it. You can't get much more direct than that. It's not like I'm citing some study to support my conclusion. These people are doing their own science and saying, well, there must be something wrong because I believe this so hard. I believe it so hard. And I'm kind of glad that they do their own science. I'm a little disappointed that they don't come to their conclusions, but I mean, because they believe it so much. Do you know what I mean? Because if there's something that you believe that much, if there's something that you really believe, you have to question it all the time. And here's where we get to the bad faith part. You can tell they're not arguing in good faith. Because if you're arguing in good faith, when the evidence shows up that says you're wrong, you say, well, shit, I guess I was wrong. The people that are out there, the flat earthers that are out there they're out there trying to prove that the earth is flat. They're not out there trying to argue that to prove themselves wrong. Because that's what you need to be doing in science. You need to be proving that you are wrong. If you can't do that, then you might be onto something. That's the other thing I like so much about this test for divergence. It's not that the terms go to 0, it's how the terms go to 0. And what are we talking about? Oh, yeah. Flat earthers are bad at science. You got to question it. The more you believe a thing, the more you have to question it. The stronger that belief, the stronger you have to attack it. You have to attack your beliefs. Always. Never just settle into your beliefs. always constantly attack them. This is the nature of being educated. This is why it's exhausting. This is why people don't like it. But you have to. There's a reason that ignorance is bliss, because knowledge is exhausting and disheartening. Anyway, what are we talking about? Oh yeah, we're talking P-series. The most important part of this problem happened like 5 minutes ago when I looked at this and said convergence. Done. That was the important thing. The reason why is so that we can apply this to more things. If I have the series 1 over the square root of n, we can immediately say that this diverges. The important part of the problem is done. As soon as I wrote D, the problem was over. Because if I stopped writing after the first letter, if you stop writing after the first letter and I say, time's up, turn in your paper, I would say, oh yeah, they were going to write diverges. If you had to justify this, you would be like, oh, this is a P series with P equal to 1/2, which is less than 1, and therefore diverge. If you were going to use the integral test, notice that the exponent is a negative 1/2, and when we add 1 to the exponent, it becomes a positive 1/2. The x goes up into the numerator, and when b goes to infinity, that term goes to infinity, and the improper integral diverges, so the series diverges. Isn't it much better to just say divergence, P series, 1/2? Now you got to be aware, don't always just do P series when there's a better answer. Don't always use P series when there's especially when there's a better answer. The series 1 over n cubed diverges. We could say this is a P series with P equal to -3, which is less than 1. But that is ridiculous. We have a better answer. Terms don't go to 0. So even though it does fit this description, it's a P series with P equal to -3, which is less than 1. Therefore, it diverges. You could say that it does fit this description, and the reason I point this out is to show you that it does fit this description, but this would be trash as a justification. You should not bring this to court. You'd be like, oh, Your Honor, opposing counsel is an idiot. The limit of the terms isn't 0. That's why the series diverges. This is why on a multiple choice test, it doesn't say choose the right answer. It says choose the best answer. This is how you know whoever invented the multiple choice test knew how cruel they were. So they didn't say choose the right answer. They said one of these is correct. The rest are incorrect. They said choose the best answer. Some of these are right. Some of them are wrong. I want you to choose the best right answer. So I would write a multiple choice test that will explain why the series diverges. One of the answers would be it's a P series of P equal to -3, which is less than 1, so it diverges. And another answer would be the terms don't go to 0. And I would say choose the best answer, not the right answer. You know what I mean? And neither one would be at position C because the answer is never C on a multiple choice test. The other thing that we can get from the integral test, we can't have 3a without a 3b, otherwise it would just be like 3. So, but I definitely want this to be like a corollaries to the integral test. Another one we can get from this is a geometric series. And has a very similar format, which is why I like putting these two together. So the series 5 times 0.2 to the n converges. It's a geometric series with a common ratio less than 1. Oops. I'll just state what the common ratio is. The common ratio is 0.2, which is less than 1. This series 5 times 3 to the n is geometric with a common ratio of 3, which is greater than 1. But this also means that the terms don't go to 0. But we could point out, because of the form, now, in this case, when we point out that this is a geometric series with a common ratio of 3, which is greater than 1, we did bring something new in this argument. We did point out that this is, in fact, a geometric series. But because it's a geometric series with a common ratio greater than 1, the terms don't go to 0. Always check to see if the terms go to 0. In this case, we wanted to take the extra step and point out that this was a geometric series. Now, in actual math court, you would not want to point out the geometric series. If the question is just that the series converge diverge, you could say terms don't go to 0, so the series diverges. Don't say anything else. Does the same rules apply in math courts? You don't respond to questions. It's your Fifth Amendment right. The opposing counsel is like, well, would you say this is a geometric series? You don't say anything. Were you doing your geometric series homework when you encountered this problem? The response is, I will not be discussing that yet. Then if they ask again, you invoke the Fifth Amendment right. Then you ask, am I being detained? Or am I free to go? As a representative of the states, you are no longer being detained. Y'all are free to go. That's going to do it for today. That's going to do it for this week. That's going to do it for this first half of the semester before spring break. Everybody have a nice spring break. I'll see y'all on the following Monday. And thanks for playing.